Okay. So hopefully we can all see this. We're taking a look at 8.4, which is polar graphs, okay? So let's kind of start off with some things that we know, and then we'll talk about what's new. And I didn't fix this part. We'll fix it right now for the polar graphs, okay? So what do we know about y equals x? What does that look like? It is a line. Yes, it is. What do we know about y equals x squared? It is the parabola, yes. What about e to the x? This is for my 116 folks. What about e to the x? Not quite. It's not a u. That would be the same as the parabola. It is an exponential. Yeah, it kind of looks something like this, right? Okay. What about our natural log graph? What does that look like? Yeah, kind of. Yeah, I see where you're going with that. It's kind of like this thing, right? Okay. What about sine and cosine? What do those graphs look like? I know they look very similar, but maybe tell me some key differences between those two. Which one goes through the origin, sine or cosine? Sine goes through the origin, yeah, so we've got something kind of like this for sine. Yeah, and then cosine, is that odd or even? It is even, and so that means that we have something with symmetry across the y-axis, okay? So these are all things that we should know, right? And you can tell that we know the line and the parabola really well. And then some of the other graphs were like, oh, I don't know, I hope they don't come up again. They kind of do, all right? So we want to make sure they're still kind of fresh in our brains. But what we're going to think about new is like, what kinds of patterns do we see for polar graphs? Because it opens up a whole new world of common shapes and equations that are really handy to know. Okay, so our focus for this class is going to be mostly on recognizing some of the sort of foundational equations and graphs. I don't think that you need to memorize them all, but I think once you get to Calc 2, right, so not Calc 1, but Calc 2, once you get to Calc 2, you're going to find that knowing these graphs is actually going to make your life a lot easier because we're going to do so many things with those graphs. Okay, so we're not there yet. And our focus is really going to be on like, where do these graphs come from? Like, how can we sort of recreate it quickly, especially if we can't remember what it looks like? Okay. And so we're going to start simple. We're going to start with some simple circles and lines. Okay. And so it turns out that if you graph r equals a constant, all right, so r equals 3, like we saw in 8.3, or r equals 5, or r equals -2, anytime you graph r equals a number, you're going to get a circle. okay? But more specifically, that circle is going to have a center at the origin. And so when you see r equals a constant, you're going to end up with something kind of like this, okay? And the number that you get, all right, whatever that number is, will give you the radius of that circle, okay? Now it turns out that we can also draw lines in polar, and the equation is fairly straightforward as well. Theta equals a number. So not r equals something, but theta equals a number is going to give us a line, okay? And specifically, that line is going to go through the origin. So you might have one kind of like this, okay? And whatever the constant is will tell you what angle your line is at, okay? And so those are sort of our two most simple equations. R equals a constant and theta equals a constant. And those are going to give us either a circle or a line, and both of those are either centered at the origin or go through the origin, okay? Now, I can tell you that, but let's kind of construct a few to make sure that we really understand, like, okay, but where does that come from? Like, how do we know that, okay? All right, so let's take a look at example 1, okay? So r equals 4. Now, based off of what we said from above, we know that this is going to be a circle centered at the origin with a radius of 4, okay? But we just learned that, right? So it's literally right above in the notes. That's not a surprise to us. So what happens if later on we're like, oh, I forget what shape that is, right? So let's kind of make a little table of values and figure out how we can get this. So if we were to choose some numbers from the unit circle, okay, maybe we could try like 0 as an angle. How about the quadrantal angles, like pi over 2, pi, and 3 pi over 2? Okay. I'm just going to pick some quote unquote nice angles. Now, at 0, what is the radius? Or what is r, according to the equation? It's 4, right? It says r equals 4. So at 0 for theta, r equals 4. Well, what about at pi over 2? What is the r? 4. Okay, so when we only have r is always going to be whatever number we have. It doesn't actually matter what the angle is, okay? So now let's think about what this looks like in a coordinate, all right? So when we write our polar coordinates, we know that it's r comma theta. And yes, Natalia, because it's a constant, okay? So if we were to write this as a coordinate, we would have 4 comma 0, right? Because it's the r first and then the theta. The next point would be 4 comma pi over 2, then 4 comma pi, and then 4 comma 3 pi over 2. Okay. And so let's plot these points. Let's plot these points on our circle over here, this graph that we have, and see, does it actually give us that circle that Judy promised us it would, okay? So I'm going to plot that first point, 4 comma 0. So I'm going to go to 0, go out 1, 2, 3, 4. Okay. Then I'm going to go to plot 4 comma pi over 2. So that's here. And then 4 comma pi. and then 4 comma 3 pi over 2. Okay. Now I know that's only 4 points, so maybe we have a square, okay? But if we were to fill in all the other angles that are on our unit circle or even not on our unit circle, we would find that we could connect these in a circle, okay? But these 4 happen to be sort of like quote unquote nice points to graph because pretty much everything is like a coordinate on our polar grid, okay? And so if we were to connect these, we could see that we end up with the circle. The center is at the origin and it has a radius of 4. Okay. So now some of these simpler ones, you might be like, oh, I know how to, like, I know what this is. I know this is a circle. You could just graph a circle. Okay. But as we get into ones that are more and more complicated, having a table is actually not a bad tool to sort of fall back on. Okay. All right. Any questions about number 1? So let's take a look at example number 2. Okay, so I've got r equals -3 root 2. Well, I mean, the numbers aren't as nice, but this sure looks like r equals a constant, right? Like a number. So from here, we can say, oh, this is going to be a circle centered at the origin. And the radius is going to be 3 root 2. Okay. And if we want to think about what that's sort of equal to, it's about 4.25. Okay, if I type that into the calculator, turn it into a decimal, and get about 4.25. Okay. Well, let's really convince ourselves though, because we want to make sure that we understand a process that will actually help us graph other things too, right? So we could pick a few angles. The quadrantal ones are usually nice ones to try first, okay? Now, what is R going to be for each one of these angles? According to our equation, what is R going to be? -3 root 2, yeah. And it's going to be -3 root 2 for every single one of these. And the y is sort of like what Natalia said earlier, because it's a constant. The radius is always going to be that, okay? So let's think about what this might mean if we plot it. So that means we have -4.25 comma 0, -4.25 comma pi over 2, -4.25 comma pi, and -4.25 comma 3 pi over 2. Okay, and I just changed them into decimals to make it a little bit easier to plot, okay? But let's go ahead and plot that first point. So I'm gonna go to 0, but I'm not gonna count out 4.25 to the right. I'm gonna count 4.25 out to the left. So my first point is actually at 1, 2, 3, 4.25. That's where my first point is, okay? Does that make sense to folks? That it's on the left-hand side, it's not on the right-hand side because of that negative, okay? And so we can kind of plot all the other points in the same way. We're gonna go to pi over 2, but we're not gonna go up 4.25, we're gonna go down 4.25. And we're gonna go to pi, and we're not gonna go in the pi direction, but we're going to go opposite the pi direction. And then for 3 pi over 2, we're not going to go down 4.25, but we're going to go in the opposite direction to get that point up there. Okay. So the negative in there, that didn't change the shape. It's still a circle, but it just changed the order in which we plotted the point. Okay. And so you can connect these. I don't think this one will be quite so nice, but we can connect these to make a circle that has a radius that is a little bit bigger than 4. Okay. So let me kind of put example 1 and example 2 up on the same screen. That kind of makes sense how we found the points and then graph the points. You can give me like a quick thumbs up or. Okay, cool. All right, so that was the first simple shape we had, right? We have a circle. We just found we could probably memorize that pretty easily, or we could plot some points just in case we forgot. But let's take a look at this other case with the theta being the constant, okay? So theta being a constant means we're not going to get a circle, but rather we're going to get a line, okay? So let's take a look at what that's going to look like. All right. So we've got theta equals 5 pi over 4, okay? So now when I fill in the thetas in my table, well, what should I write down for all my thetas? That it's constant, yeah. And so I don't want to put in 0, pi over 2, pi over 4, but I want to put in 5 pi over 4 for every single one of them. Okay? So what I've done here is said theta is going to be constant now. So we don't want to go all the way around the unit circle. We're only picking 5 pi over 4, right? But for the r, now we can choose whatever we want, okay? So let me just choose a few numbers. I'll choose like -5, -2, 0, and 3, okay? I'm just choosing some random r's. Now, if I think about the coordinates, here's what I've got. I've got a bunch of coordinates that all have the same angle. Okay, they all have the same angle. Now let's plot these points and see, like, do we get this line that Judy promised? Okay, so let's start off with -5, 5 pi over 4. So I'm going to go to 5 pi over 4, which is down here. And I'm going to go -5. So that's going to be 1, 2, 3, 4, 5. Okay, so -5, so it's in the opposite direction of 5 pi over 4. Okay, now when we plot -2, 5 pi over 4, it's in that same direction, but it's only out 2 circles. 5 pi over 4, 0 is going to be right there because I'm not going out any circles. And then 3, 5 pi over 4 is down here. Okay. And so now if we connect these dots, I think we have a fairly convincing argument that we have a line that goes through the origin and it's in the direction of 5 pi over 4. Okay. Does that kind of make sense to folks? Okay. All right. Do we want to see one more example of the line, or are we okay with that? Well, I might leave this one for you to kind of try on your own, okay? Think about the process that we went through to get those, and then think about like knowing sort of these basic equations, what might that look like, okay? Well, maybe it would be a better use of our time right now to take a look at even more types of polar equations and graphs, okay? So it turns out that we can have a bunch of different circles, okay? So we can have a center at the origin. That's what we did. It's just r equals a number. But we could have r equals a cosine theta or r equals a sine theta. And when we see those equations, those are actually going to give us circles, but the center is not at the origin, okay? So let me just write this up here that the center is not at the origin, okay? And I'll tell you what these look like, and then we'll sort of go through a table to really convince ourselves that this is indeed what it looks like, okay? So r equals a cosine theta. Now, a is going to be a number, 2, 3, -5, 14, but a is going to be a number, okay? And it turns out when we have a number times cosine theta, we're actually going to end up with a circle that is symmetric about the x-axis. Okay. And one thing that is different about this circle is that A is not the radius, but A actually tells us the diameter of the circle. Okay. Now what that means is this point out here is going to be A comma 0. Okay. And our center of the circle is going to be A over 2 comma 0. All right, so A is the diameter, is not the radius. It's not the radius. Okay. Now, if we have the equation R equals A sine theta, turns out that's going to give us a circle that is symmetric about the y-axis. Okay, so symmetric about the y-axis, but the same thing holds true that A is going to be the diameter, not the radius. Okay, and so we could label this top point as 0 comma A and the center as 0 comma half of A. I'll give you a moment to copy that down, right? But our new thing is we've got other ways to say circles, and the way that they are symmetric is different, and that's something we can actually tell from the equation, okay? So if we have a cosine in there, it's going to be symmetric about the x-axis. If we have a sine in there, it's going to be symmetric about the y-axis, okay? So let's do an example where we actually plot some points and really convince ourselves that this is actually true, okay? So let's start off with this one. All right, let's start off with example 5. So example 5 says that we have 5 cosine theta. So according to our table above, we know that this is a circle with a radius of what? What is the radius of this circle going to be? .5, good. So we know it's going to be half of the a value, okay? Now, is it going to be symmetric about the y-axis or symmetric about the x-axis? It's going to be symmetric about the x, okay? Now, I'm writing in the same color, so that's like a clear giveaway, right? Like we know it's going to be the same as the orange one above, but these are all sort of important details to think about when you are plotting these, right? Now, some of us are great at memorizing, so this is no problem to memorize. But when we're learning all this other math and layering on other things, it might be useful to think, okay, how could we go back to a table to sketch it out real quick, just so we know, okay? And so what we're going to do here is you'll see that this table is a little bit bigger than the other ones, right? And it's a little bit longer for a good reason. So we're going to try plugging in the regular values we had before. 0, I'm going to skip a line, pi over 2, pi, 3 pi over 2, and 2 pi. Okay, so I've skipped lines in between because let's see if these quadrantal angles give us an idea of what's going on. Okay, they worked for us before. Are they going to work for us now? So now if I plug 0 in for theta, okay, into this equation, 5 cosine theta, right? I'm going to get 5 cosine 0. What's cosine of 0? It's 1, yeah. So when I plug in 0, I get 5 cosine 0, which is really 5 times 1, which will give me 5, okay? This is really where we're going to be using unit circle stuff in calculus, okay? So when we get to calculus, it's a lot of knowing like what's cosine of 0, what's cosine of pi over 2, what's sine of 0, what's sine of pi over 2. So really knowing those unit circle values is going to be helpful, okay? All right, what happens if we plug in pi over 2 for theta? What does our r equal? So I plug in pi over 2. I have cosine of pi over 2, which is 0, and 5 times 0 is 0, okay? All right, we plug in pi. I get 5 cosine pi. That's 5 times -1, which is -5. I plug in 3 pi over 2. I'm going to get 5 times cosine of 3 pi over 2, which is going to be 0. And I plug in 2 pi, and I'm going to get cosine of 2 pi, which is 1, and 5 times 1 is 5. Okay? When you get to Calc 2, your professor is going to go through that a lot faster. Okay, so we're sort of in this, we're just finishing up trig, but I don't want you to leave this course thinking that's the end of it and you never need to know all this stuff again, okay? There's a reason we have a whole course dedicated to this and being good with the unit circle because it does come up frequently, okay? So let's write out these coordinates to kind of see what we have. So we have 5, 0. We have 0, pi over 2, -5, pi, 0, comma 3 pi over 2, and 5, comma 2 pi. All right, and I'm going to plot these on the grid and kind of see where we're at. So 5, comma 0 is 1, 2, 3, 4, 5. That's the first point. Okay. Then I go to pi over 2, comma 0, or not going up and out at any, so that's going to get me back to here. Okay, so far I've plotted the first 2 points. We good with that? Yes, no, yes. Okay, then we have -5, comma pi. Where is that point going to be? If you can sort of draw on the screen, go ahead and draw it. Where is -5, comma pi going to be? Perfect. Yeah, it's exactly where Thea marked it, and Natalia and Ethan. So all of those are back at the first point, right? Where would 0, comma 3 pi over 2 be? Yeah, it's going to be right back at the origin. And if I go to 5, comma 2 pi, it's going to be back at that first point. So even though I put in 5 points into the table, I only got 2 points out. So maybe I would think the graph maybe looks like that, right? That's a valid prediction. But that's sort of why I left some spaces so we could fill in some more blanks and figure out what does the rest of this look like, okay? So sometimes the quadrantal angles are enough, and sometimes we need some of the other angles to help us out, okay? So let's go with pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. So let's bring in some of those other values to help us figure out what it is, okay? So if I put pi over 4 in for cosine, all right? Yeah, you could remember it now. I want to make sure you've got some fallback tools for later, okay? So pi over 4, I plug that in. I'm going to get 5 times root 2 over 2, all right? So a weird number, but let's turn that into a decimal and kind of see what we get. So 5 root 2 divided by 2. So this will give me about 3.5, comma pi over 4, okay? So let's plot this point before we find all the other ones. So I'm going to go to pi over 4, and I'm going to count out about 3.5 circles. So 1, 2, 3, 1, 2, 3.5. Okay. So now I know with this new point that it's not going to be a circle, or rather it's not going to be a line like we thought, bouncing back and forth between 2 points. Is it a triangle? I don't know. So let's find some more points to plot and figure out. Okay. So let's see. Cosine of 3 pi over 4 is negative. So that's going to be -5 root 2 over 2. So we'll get -3.5, comma 3 pi over 4. And let's plot that and see what we get. So I'm going to go to 3 pi over 4, but I'm going to count in the opposite direction. 1, 2, 3.5. Okay. So we know we don't have a line. We know we don't have a triangle. We might have a square. I don't know. I've only got 4 points. But we're going to fill in the other points. We're going to plot some other things, and let's see what we get. So cosine of 5 pi over 4 is going to be the same as that one. -3.5, comma 5 pi over 4. And that is going to be 5 pi over 4. That's actually going to be back over here. Okay. And This one will be, and that will be 3.5 comma pi over 4. Okay. Now, let's go ahead and sketch out the circle, okay? But let's kind of follow the points that we have here, okay? So this is going to be point 1, 2, 3, 4, and 5. Okay, so let's go through those 5 first. It's like you know, connect the dots. So I have 1, I have 2, I have number 3, point 4 is down here, and point 5 is back there, okay? So if I try and draw this, I've got a circle-ish, okay? Now, I know this is a stupid question, but I want you to think about this. Do I have the whole circle here? Yeah, we have a whole circle, right? We started at 1, we got back to, and 5 was the same place as 1, so we got the circle. Okay. So this is going to be really important when you get to Calc 2, okay? That sometimes you don't need to go 0 to 2 pi to get the whole shape. Sometimes you only need to go 0 to pi to get the whole shape, okay? So what happens is when we do 0.6 and 7 and 8 and 9, we actually go over the circle again, okay? So the first half, this actually gives us the circle, and this part gives us a second circle on top of the first one. Okay. Okay, so your question, why is 0.5 where 0.1 is? Because it's exactly. So when we're looking for -5 comma pi, I go to pi, but then I go 5 in the direction away from pi, which gets us back to the point where 1 is. Okay. Okay. So we have a circle. The radius is 2.5. It's symmetric about the x-axis. All of that is stuff we could have remembered from the equation for sure. Now we got to think, okay, how can we sort of use that table to help us out a little bit? Okay. So if you're going through these questions and you're like, yeah, I'm good to memorize them, feel free to memorize them. Okay. I want you to understand how to make a table too, because I think that's a really good fallback skill in, like, 2 courses when you've learned so much stuff in between. How are you going to be able to come back and really remember these things? Okay. All right. So we've got a circle here. Let's take a look at this one. Okay. So given this equation, what do folks think this shape is going to be? Tell me about some important characteristics about this based on the equation. Okay. It is symmetric about the y-axis. I love it. Okay. And we should know that it's a circle just because it's like an r sine theta. Okay. And what about the radius? Because that's also important as we sort of think about characteristic. Okay, what's the radius of this circle going to be? Yeah, that radius is going to be 2. Okay, so the radius is not 4, but it's going to be 2. And that part is really where, when you're in Calc 2 and you're sort of sketching things, it might be nice to do just a quick few values in a table to make sure you get the right radius and you don't get the diameter by accident, okay? So let's think about some values again. Let's use the same values that we had from the previous table. Oop. And let's plot some points, okay? So if we're putting in our betas, let's see, sine of 0 is 0, so that's going to be 0. We've got 0, comma 0. Sine of pi over 4 is root 2 over 2, so negative 4 times root 2 over 2, which gives us negative 2 root 2. And we can turn that into a decimal. Negative 2.8, comma pi over 4. Okay. And we can keep going through all these values, all right? And as you can tell, yeah, this is kind of a lot of work to put in all these different values, okay? So as far as David's question about going up to pi or going all the way up to 2 pi, so here's the thing. Sometimes you're going to have to go to pi to get the whole shape, but sometimes you're going to need to go to 2 pi to get the whole shape, okay? So that's something that, as we're sort of doing this for the first time, I would like us to kind of start to think about what patterns we see, because when we get to Calc 2, I would prefer that you don't sit and write out all the numbers all the time, okay? So start to think about, do I need to go to pi or do I need to go to 2 pi? And you'll be able to tell. You could go to pi, see if you get your whole shape. If you did, you can stop, right? But if you only get half of it or you're not sure, you might want to keep going until 2 pi, okay? So let's kind of crank through the rest of these. Let's see, sine of pi over 2 is 1. So negative 4 times 1 is negative 4. And maybe let's just plot these first 3 points and see what we have, okay? So our first point is going to be at the origin, 0, comma 0. Then I'm going to go to pi over 4, and I'm going to go negative 2.8. So 1, 2.8. All right, then I'm going to go to pi over 2, and I'm going to go down 4. So 1, 2, 3, 4. Okay. Why is r 0? Because when you put in 0 for theta, sine of 0 is 0. Negative 4 times 0 is 0. Right. And Yithan, go back and look at the top table. That is not the correct thing, right? So it's not symmetric about the x-axis. Right, because that's when we have cosine. This is not cosine. This is sine. Exactly, right? And so this is where you can see that, even 20 minutes in, we're already like, wait, which rule is it? Which symmetry is it? So that's why sometimes it's helpful. As soon as I plot these points, these 3 points, I already know it's symmetric about the y-axis. right? So even if I forget, just by plotting 3 points, I'm like, this is symmetric about the y-axis. So it's a good reminder about those different rules, okay? Because it is a lot to memorize for sure. All right, so if I know that it's symmetric about the y-axis, I can actually plot the other point on the other side, the 2.8 at the 7 pi over 4, because I bet that's going to be another point if I fill out the whole table, okay? So the symmetry actually is super helpful in sketching it, because you guys are right. Sometimes we don't want to fill out that whole table, right? And sometimes we do want to fill out the whole table, and it is more useful. But it's just a tool to kind of help us remember some of these different rules, okay? So we have a circle, the radius is 2, it's symmetric about the y-axis, matches up with everything that we talked about before, okay? But if we look back real quick at the other one, I said that if it's a sine theta, that it was a circle symmetric about the y-axis, and the one I drew was on top of the x-axis, right? But how come ours down here wasn't on top of the x-axis? Yeah, good, good. So that's like one of those other patterns, right? If the number in front is negative, it's not going to be on the top, it's going to be on the bottom if it's sine, okay? And what if instead of 5 cosine theta, we had negative 5 cosine theta? Where would our circle be? Okay. Yeah, it would be on the left-hand side of the x-axis. So when we think about making things positive or negative, it does sort of change where it is, but it doesn't change the symmetry. Symmetry is still going to be the same. Cosine is going to have symmetry about the x-axis, and sine is going to have symmetry about the y-axis. Okay. All right, so we sort of use some tables to plot some things, right? But it turns out that there's actually a bunch of other shapes too, okay? So there's one called a Limassons, and there's one called rose curves that you'll sort of see towards the end, okay? So we've got Limassons and rose curves. So what we're gonna do is we're actually gonna stop here for today. So let me just stop sharing my screen. And okay. What I would like us to do is, if you're still in Canvas, if you could open up classwork number 6, okay? So classwork number 6. So when you open up classwork number 6, the rose curve is the one that looks like flowers, yes. Yeah, I think they're pretty. Okay. So if you open up classwork number 6, let me just share my screen so you know what it looks like, okay? Okay, can you all see the one that says patterns with polar graphs? Yeah, okay, cool. So this is gonna be on your own time, okay? This is gonna count as classwork number 6, all right? And so this is your handout. You don't have to draw anything on here. You can go ahead and screenshot the graphs that you get from Desmos and put them right in here, okay? I'm assuming we all know how to screenshot. If you don't, ask a friend. I'm sure someone can help you out with that, okay? But what you're gonna do is if you go back to the classwork, there's also a link to a Desmos activity, okay? And so all the questions are asking you to work with this piece. You go problem set by problem set. So problem set 1 is like the first few questions. When you're done with that one, you can kind of close it and you can open problem set number 2 and problem set number 3, okay? And they're going to ask you a series of questions, like you're going to play some of the animations here, see what happens as different numbers change, okay? So you can stop it whenever you want, or you can move the slider to be whatever equation you're trying to match it for. And once you've got your picture, you can go ahead and screenshot that and put that picture right into the handout for the patterns with polar graphs. So kind of like the other activity we did earlier, you're going to save a copy for yourself. You're going to insert your screenshots in there, and then I'm going to ask you some questions that are like, what are these things that the graphs have in common and what's different to them? But more specifically, how does the equation kind of tell us what's happening with the graph, okay? So play around with this. Some of this is going to be review from the circles that we learned in class today. Some of this is going to be looking at the flower graphs, so the rose curves, and some of them are going to be looking at the Limassons, which you'll see what those look like in when you get to those, okay? So this assignment is due Wednesday at 5 o'clock, but I think it would be a great idea for you to do it before class on Wednesday so that when we go through the rest of this lesson, it'll be a little bit quicker because you've kind of already thought about what we're gonna do, okay? Does that make sense, folks, in terms of how to do this particular handout and the activity that goes with it? Okay, I've got a couple yeses. Yes, okay. Well, if you have any clarifying questions, definitely ask. But we've got classwork 5, which was the matching ones with the those cute animals and scarves and things. And then this one, which is using Desmos to really help us figure out what the patterns are. Okay, so one of those is due at 5 o'clock today. The other one is due at 5 o'clock on Wednesday. All right. And we'll pick up with this on Wednesday, and then we'll start also taking a look at another kind of graphing. I mean, I hope you did it. So yes, completion, but also your answers should be right. So if they're not, you might want to go back and double check those. Okay. All right. So folks, we're going to end things here.